All right, so we are live and we have our community forum ready to go. So thanks everyone for joining us. We already have a couple of viewers in the stream talking about pins. Maybe we can elaborate on that a little bit later. And the idea of the community forum is to just have a little bit of a touch base with what's happening in a broader context. So we've been doing a lot of live science recently, chasing down various scientific endeavors and trying to get some proper research done. And this is just a moment to kind of zoom out a little bit and discuss a bit more broadly, what are we doing in our various little directions, and to zoom out and see if there's some interesting insights that can inform all of our individual efforts. So that's the idea. So yeah, we've got Carlos, Nick, and myself, James. Carlos, you were talking a little bit about a recent event that you attended. Maybe we can start there, and we can discuss broader topics as we progress.
Yeah, certainly. Well, it was an exciting morning for me. I went to virtually attended the Bell Labs seminar. I was invited there to give a talk, and this is the European branch of Bell Labs, and I was presenting a talk on what I called hypergraph computation. I mean, it was, for this audience, very well known and nothing new, but it was interesting because the head of Bell Labs at the end followed up and said, so here at Bell Labs, we have people working on all sorts of new ways of computing, quantum computing, analog computing, distributed computing. But he said, hypergraph computing is new to me. This is I didn't hear of this before, and it was intellectually stimulating to see how you could connect matrix multiplication and sort of tensor-like operations with these rewrite systems and so on. I even dropped maybe I'm losing millions of dollars in the future for saying this out loud, but the idea to encode edges in qubit entanglement. And the fact that you don't, I dropped this idea that maybe, the instability and short-lived duration of quantum states might be okay if you have an architecture that basically allows you to classically encode a hypergraph, some Boolean information, and then it translates that Boolean information into some set of entangled qubits, and then some quantum computation happens, which the magic of it works in such a way that you can know that certain rewrite rules are being applied to the classical hypergraph, and if you design your rules correctly, you don't need to know what rules in what order are being applied. You just care that things are being applied in all possible ways, or at least in one direction, and so you don't care. In fact, you care that things are as fast as possible and things are as short-lived as possible, as long as the thing is being implemented. This is fantasy. I don't have any actual implementation in mind. But the idea that qubit entanglement could encode something like hyperedges. This I dropped at the end of the talk. I presented the idea of hypergraph computation as a sort of alternative to matrix. To tensor or array computation. And I think the argument is very compelling, because you clearly show that you can do both things if you have a hypergraph data structure or you have an array data structure. And the moment that you entice the possibility.
Can I comment on this?
Of course.
It's just because maybe we'll go in to talk about something else. But this, like, entanglement and hyperedges, you can actually think of quantum computation in general as actually manipulating some hypergraph in actually very straightforward way. It's like, because when you have like a qubit string 0001 with some amplitude, if you just encode it as a hyperedge, right, because for example, you have a vertex for each qubit, okay, and
sure,
and you just basically you make a hyperedge and it just weighted. By default, it's a complex weight, but you can do like some basis transformation and make purely like real weights with some negative sign that you can also make like to represent by some direction of the hyperedge. And you can like represent all the computation by just manipulating these hyperedges with multiplicities of weights as minimally. Like write this hyperedge to a different hyperedge. That's like what quantum operators actually look like. That's the input, that's the output, that's an additional factor that you have to multiply, that's just adding some more edges.
Interesting.
But
So is the
Yeah.
computation diagrammatically presented like that in quantum computation now or not yet?
No.
No, it's not very useful. It's like it's very, very dense hypergraph. It's like, imagine like if you just started with a complete uniform superposition, it basically means you have a very giant tensor, and it's like contains some number in every element of that tensor. And if that tensor is your adjacency tensor of the hypergraph, essentially, it's just like you having an edge, any possible edge, basically. It's just not very useful.
Interesting.
Right. Yeah, that's interesting. I mean, what I was posing to them is, you have to believe that there is a problem for which hypergraph computation is particularly efficient, and this is really the engineering side of it. Like, if you have, I can only imagine that there are some systems out there which are very network based. Like they have some kind of network structure or a high order network structure, and I can only imagine that there might be some computations about those networks that might be much more efficiently implemented with some kind of rewrite framework. So assuming that that's the case, and that's a big if, but assuming that's the case, I was thinking, maybe quantum computers, like we don't use quantum states. That's not the point. We still want classical states, but maybe the quantum processes that they're really not. I mean, they're just processes in the quantum sense, right? In physical sense. As long as you can be sure that you are encoding your hypergraphs with some form of quantum state, and you can be sure somehow, and this is a very interesting technical question, how you would actually make that connection. If you can make sure that the certain rewrite rules are being applied, but not others, and you can have kind of your miniature, then you would have this kind of like units of hypergraph processing, which are sort of quantum in nature, so quantum in process. Like you have some qubits, they interact, they unitary evolve or something, right? And only after a while you can sort of collapse and get a Boolean state again of that system. And anyway, this was the premise, and we can still claim that head of Bell Labs Europe was enticed by this idea. So this is a claim to our efforts here. So that was one thing that happened this week for sure.
Very nice. Yeah, are those presentations going to be available, or is there a recording?
No, it was all private. But again, the presentation doesn't. I mean, for our community, people who know what we do, it didn't. It was just it only contained a final slide that is not in other presentation that is already public, and that slide only contained these open questions about, what would be a good substrate for hypergraphs, is qubit entanglement an interesting option to do higher order data structures, and I find it interesting because you really want to have hypergraphs be more or less classical Boolean states. I mean, otherwise it doesn't make a lot of sense to say that you store information in some sense, right? Like, in what sense, you want to operate that classically, you want to have that compatible with the rest of your architecture in a classical computer and everything. But what I find interesting is that entanglement naturally seems to have this higher order nature to it. Right? Entanglement is this sort of more or less symmetrical involvement of several units. And so I find it interesting that since you only really require that your edges be mutable, right? That it might change when they are in process, right? They are being rewritten or they're being somehow evolved. It seems to me that the advantages of quantum computing, which have this notion of if you observe, you destroy it, right? Like if you interact too much with it, it goes wrong. It sounds to me that if you somehow can concoct, that you can prepare a system that through unitary evolution or through sort of quantum dynamics, where higher order entanglement of qubits corresponds to the hyperedges in a hypergraph. Is there a sense in which you can say that unitary evolution of such qubits will give you something like implementing a hypergraph algorithm? I'm not even saying rewriting, but some kind of hypergraph algorithm. I don't know. It's a very silly thing to pose, but I mean, Nick already mentioned this fact about how you can naturally see entanglement as a hypergraph, and you know,
No,
I don't know.
just general quantum. Yeah, just general quantum state.
Yeah, general quantum states for sure. Yeah.
Because just any quantum state is just of multi-system, is just tensor, and hypergraph also have a tensor representations. So you just make this connection between them, and you're ready to go. To rewrite your hypergraph is essentially the same as doing quantum operations.
Yeah, exactly. So anyway, I find it interesting. I don't know if that's going to prove useful in practice, like obviously. And then there's a big question of what problems will be solving. Like the way I imagine a hypergraph computer being useful is essentially the same way that a GPU is useful nowadays, right? You have your architecture over there, and then you have your unit that is specialized in a certain type of computing. You know, your central processor has a lot of Boolean gates and a lot of like parallel, like well, not parallel, but like all these branchings and, you know, logical branchings and things like that. Your GPU has all this very large parallel array sort of linear operation, and maybe you would have something that is much more networky in infrastructure, right? And because the funny thing to me is that, you know, all this machine learning explosion and all the, you know, NVIDIA going to the moon and all this stuff with the GPUs, to me it sounds like, yeah, a lot of the systems definitely need a lot of parallel computation. That's why GPUs are powerful. But there will be some systems where it's parallel, but in a certain sense, right? It's not just parallel in general, but it's parallel in the sense that it's network parallel, which is not, I mean, usual parallel is like a range of topologies, a range of network topologies that are kind of like grid-like, or they tend to be very, what is the word? Regular in technical terms, in technical network terms, right? You might not have regularity. You might have very complicated hypergraphs. Like think of a brain, right? And this is the sort of there's the bio-inspired computation, right? So this is part of, I would say, thematically of that. Like in a brain, you don't have an array. You don't have an array structure. Somewhere in the brain, you can find array-like structures for sure, but generally, biological computation, like neural computation, natural neural computation, is very much, you know, distributed, higher order connectivity kind of things. And if you think of the role of the glial cells around the neurons, these are very much like hyperedges connecting synapse nodes, right? So anyway, just to say that it seems to be very plausible. I don't have the proof for it. I don't know for sure, but it seems to me very plausible that there will be some regime of problems that we humans care about that are very much native to this sort of network language, to some kind of natural network language. And hypergraph computing is basically that. It's basically network computing in a very abstract sense, right? In a very general sense.
So just I didn't realize that about the glial cells. Couldn't neurons and like neuron firings be described purely in terms of a graph, like a conventional graph structure? Where does the hyperedges help in description of neural connections?
When I note that I don't really say hyper, I just say network. Right?
Okay. Yeah.
I'm not even specifying. The point is, when I say hypergraph, I don't mean strictly hypergraph. I mean graphs in general, right? Like I don't say, oh yeah, you have to consider ternary edges at least, otherwise you're not in the cloud. You know, you're not allowed in. Like, but you know, we currently, I mean, even if you just wanted to do matrix dynamics and just network stuff, we currently don't have chips that natively run rewriting algorithms. Right? Yeah. We have chips that run Boolean algebra, right? And obviously there's universality of computation allows you to run everything, of course, but we don't have native rewriting chips in a sense of native network rewriting chips, right? So this hypergraph computation is.
Could you think of a rewriting as a matrix multiplication in any way? Is that possible, or not necessarily? No.
Not so you can bring out matrix multiplication as a very special case of rewriting, but not the other way around. Like matrix multiplication won't be like it's too high level. It's too sort of user level, mathematician level structure. We want something that is more infra, right? Going using our sort of institute branding of things.
Maybe like DNA computing is more like rewriting. Actually, like
exactly
going into some. Yeah.
Exactly.
So you have a DNA molecule floating around, and you have a bunch of them, and you just go around and just point, just to write some piece of it.
Exactly. And in fact, when I was thinking of what would be examples of hypergraph computing, my first candidate, before I thought of this qubit entanglement meme, I thought of biological systems. I mean, cells are essentially doing that, like chemical reaction, not even cells, but just chemistry in general. Especially polymeric chemistry seems to behave a lot like rewriting, where you have units and they sort of splice in certain locations, and enzymes quite literally apply rewrite rules, right? Like an enzyme arrives and like attaches at the site and then just does something. And this, it's very, very rewrite-like, and obviously just the whole genetic code system, right? Like you get your RNA and you read off the protein and so on. Like it's all very much a sort of writing and rewriting process, right? Both at the abstract level of the code, of the genetic code, but also the molecular level of the sort of substrate. But it's doing that kind of thing.
It's just the problem that it's like statistical in nature. You always have an ensemble of all many molecules in like one petri dish, and then your rules is essentially like you throw something in that petri dish and then just wait till equilibrium or something, right?
Exactly.
And then you read out statistics, what kind of the new molecule you get.
Exactly.
I was kind of I had this idea that essentially if we had a molecule DNA computing of this sort, with like when you can actually rewrite this long strands. In this way, you can actually simulate quantum computer with it more efficiently than current conventional classical computers can do, based on logic and transistors. Because you exactly require the same kind of thing in there when you have a bunch of statistics as a single molecule like DNA, like maybe 100 enzymes alone or something. It represents like a giant probability distribution, right? Because they can be all possible different values on top of them. So it's kind of the same way when you have multiple qubits. So, and it's kind of the same way you can represent the statistical power that quantum computer provide with the same system. Yes.
Yeah. No, I agree. Both quantum and biological, in this sense, take us to this more probabilistic mindset where you're thinking of ensembles of entities that are being operated. So I think people are talking about that. I mean, obviously there's the work of this what's it called? Assembly theory, and looking at chemistry, like temporal lines of assembly theory, of assembly, molecule assembly, and things like that. Obviously, complexity theory applied to chemistry and things like that. There's some trace in history of these notions. Maybe I wanted to mention before we move on and really become excited with our transversal topics of discussion. We can make a couple of announcements now that we have a gathered audience and we seem to be all here in the community. So next week, on the topic of precisely hypergraph and computation and equivalence to matrix operations and tensor operations, we are hosting online a whole workshop on this topic. So next week, Monday to Wednesday, we are going to be hosting online this workshop. So let me bring this up on the screen. I think if I share, everyone will be able to see, right, James?
Yeah.
From your side? Yeah. Give me a second. I need to bring the page up. if I share this. You can see this, right?
Yeah.
Okay, so this is a follow-up from last year's. We had a small scale but very successful workshop where we invited some people who were working on the, generally speaking, on the topic of hypermatrices. So tensor algebra, people doing higher arity algebras, people doing hypergraphs applied to discrete mathematics and questions in these kinds of matrix algebra settings. And this year we basically just continued with the workshop and did sort of edition 2. But this time I will be in Paris. I will actually be on site and connecting to the live stream. So we are setting up a Zoom call where participants can join. So if you are interested in directly interacting with the speaker, so by the way, so this is the plan. So next week, these are local times. So these are Paris times. So you have to think that this is UTC +2 right now. So this should be morning for American times, and should otherwise be accessible to most time zones. That's where we chose sort of European afternoon time slots. So basically on Monday we have a algebra focus day. We're talking about ternary algebras mostly. We have Richard Kerner, who is one of the leading researchers on ternary algebras and non-associative algebras applied to physics, theoretical physics. We have Borowicz, we have Abramov, we have these two collaborators that actually found some of the higher ternary axioms of hypermatrices, the things that we've discussed before. People might remember the fish operation and things like that we've mentioned in some past live streams. So Monday is going to be focused on that. It's about algebra, basically. Tuesday is about hypergraphs. Basically, we are going to be talking. I'm very excited to have Nicolas Baer be one of the speakers. So Nicolas Baer is actually based in Paris. Nicolas Baer is, I would say, in my opinion, the leading expert worldwide on hypergraph rewriting.
Wow.
I would obviously Nicolas is on the side of category theory. They are interested in implementing graph rewriting frameworks with certain motivations that don't align fully with ours, which is a good thing, obviously. But I would say if I had to pick one person who understands hypergraph rewriting in a mathematical way, I would say Nicolas Baer is the leading expert worldwide. So it is true that there's not a huge community of such people. So it's not that he's like standing out of like hundreds or thousands of people, but he's definitely a very important figure. He's written some of the papers on this topic, which is I'm very glad that he chose to speak about, which is compositional rewriting, which is this idea that you can get a sense of rule self-composition. So basically the idea of how you apply a rule to itself, thinking how it's going to interact with itself. So Nick and I had a conversation yesterday about really thinking hard about what it means to rewrite and hypergraphs and so on. And I think Nicolas has some really nice ideas. So it'll be great, Nick, if you can be in that session and maybe take as much as we can from Nicolas and see what we learn. And then on that day, so early in the morning, there will be Lyubov, who is my guest, my host there in Paris. She's the one inviting me and the co-organizer of the workshop, where she's going to talk about some applications of hypergraphs to some network science data. And then in the evening, we have Francesco Lotito, who is the developer of Hypergraph X, which is the leading piece of software that could compete with our hypergraph packages. Right. So, and I talked to him before, and we have a pretty nice relation, and we are obviously in very good terms, and always discussing how we're going to solve the problem of general symmetry of hypergraphs and things like that. Like it's a nice addition. So Tuesday is really I'm quite excited about Tuesday because it's the first time that we are officially at the Institute hosting leading figures in hypergraphs, in hypergraph science, so to speak, around the world. And then finally on Wednesday, it's the day where my particular approach to this question gets more represented. So I will be presenting Plex diagrams, which is an idea that it's really historically what brought me to hypergraph rewriting in the first place. So it's a nice kind of completing the circle moment for me, where, you know, I think almost 3 years ago now, I started to think about this hypermatrix operations as examples of ternary and higher algebras. And I started to draw some diagrams that represented the index contraction. And, you know, I developed this thing called Plex diagram, which I will explain in this talk. So I will not give you any spoilers here. But essentially, they are hypergraph diagrams to represent index contraction. And many of you have seen them before, of course, in my presentations. And then we will have Josh Gruchow, which is my collaborator in the research project about the Bhattacharya-Messner product. So these terms, some people in our audience might have heard before. This Bhattacharya-Messner. This is a very mysterious ternary product that you can define very simply in terms of cubic matrices. So n by n by n arrays, and it is the direct generalization of matrix multiplication. So we have a first possible candidate of a proof that the product itself does not satisfy any term identity, which is exciting in itself, because we might actually be close to claiming that the product itself is extremely weird, right? Like it really becomes quite weird the moment that you go to ternary, and which I think will somehow attest to the difficulty in progressing in these kinds of fields. And the reason why you don't hear of the annual international conference on ternary structures or hypermatrices and so on, it's because it's a very barren research field, right? It's a very difficult to navigate field. There's very little reward from investing research hours into it. Of course, that's a job for the institute. Here we are pioneers. We like to venture into very dangerous and unknown territory. But for traditional academia, for more traditional research institutions, this is a no-go zone, right? Like they wouldn't go there. So anyway, this is you have the abstracts here if you're curious to know a little bit more about it. So what you should do if you're interested in interacting live, so this will be live streamed on YouTube where you are now. So if you tune in next week in this same channel, you will see it, and it will be recorded there for your later enjoyment. But if you want to participate and ask any questions, I would also recommend that as institute members follow this link and register, so you have an extremely short form to fill, just your name, your email, and which days you want to be considered for the Zoom call, and that's it, right? So it's very simple. It's free. Anyone can get into the calls. If you happen to be in Paris by any chance, we will advertise for the registered people. We will advertise the exact location of the seminar. It's going to be a very small group of people, mostly Richard Kerner, who's also given us the location very kindly, Lyubov and Nicholas, possibly. They are in Paris. The rest will be joining online during the workshop. So yeah,
is that local times for Paris? What are these times?
This is local Paris time. Okay. Yes. So this is UTC +2. But don't worry. We will make events on the Discord for the sessions. And actually, if you go to the Discord, our own Discord here in the Wolfram Institute, you will see that we already have a category below topics. You'll see Hypermatrix Workshop 2024, and you can see you have general questions on all the sessions. So I'm just tagging everyone there, so you can see what it is.
Cool.
So yeah, that's the Hypermatrix workshop. Very excited for next Monday.
Sounds great. Monday, Tuesday, and Wednesday. Nice.
Yes, that's Monday, Wednesday, and Monday, Tuesday, and Wednesday next week. Great.
Okay. Oh, we have a question here. Maybe this can lead us to some additional thoughts. And this is unrelated to the hypergraph workshop, but this is from D. Are anyone familiar with Mobius inversions and how they might be described by hypergraph rewriting?
Mobius inversion. Should I know about this?
Well, sounds familiar.
Yeah, same.
Yeah.
Mobius inversion. This sounds like number theory. Yeah, it is number theory.
This is obviously related to matrices in terms of the movies as well, because Mobius is the one who was a central character there.
What am I learning? I never saw before today.
What is a Mobius inversion?
Relation between pairs of arithmetic functions. So on that basis, without knowing the details of what the concrete definition of Mobius inversion, maybe the commenter can expand on where they see the connection between arithmetic functions and hypergraphic writing. I mean, I can see obviously ways to go back and forth, but I'm sure, especially such a technical thing.
Mobius transform looks like quite an interesting image.
Yeah, but Mobius transformation is a complex plane transformation. So it's that is, I understand what a Mobius transformation is, and the connection to hypergraphs is much more tenuous, but the arithmetic functions, that's actually kind of interesting.
So Dugan was saying,
hey Dugan.
Yeah, hey Dugan. Mobius inversion on the complex plane, Riemann sphere, was a question. There was a
so Dugan is bringing up a Mobius transformation, right? A Mobius, yeah.
Mobius inversion is saying different. Yeah. We'll add it to the
research. This inspired a thought, which is natural hypergraph arithmetic differs from integer arithmetic. So let me put it this way. Imagine a hypergraph. Imagine a world where you only have one vertex or two vertices, and really you only can populate the space between two vertices. So basically just pairwise edges thrown between two vertices. That's essentially a model for the integers, right? Because that's basically saying like you have a set with oh yeah, I can start sharing this actually. If you leave that on the screen, that'll be very cool. Yeah.
We can bring up a whiteboard if you want to draw some pictures for us.
Not necessarily now. I'm just thinking that, if you think that your prime computational objects are, imagine how you invent a calculator, like an analog calculator, right? Like an abacus or something like that. You're essentially using the properties of sets or multisets in some sense, right? Like you're doing addition by doing union, and you're doing iterated addition, and so on. So if suddenly your substrate is like this idea of set theoretic constructions, right? Like union and so on. But if your substrate is suddenly hypergraphs, and by the way, what you end up with is arithmetic. You sort of build up the naturals, you build up and you construct all these abstractions. But if you begin with hypergraphs, then I would say your abstractions are obviously different, right? Like the hypergraph arithmetic seems to contain ordinary arithmetic, but in this kind of simplistic settings where you only have like one vertex and unary edges there, or just a couple of vertices and just binary edges between them. But hypergraphs, by the way, this connects with, so I've always thought of hypergraphs in the last 2-3 years when I've been working with them. I've always thought of hypergraphs as sets with thrown in information, right? Like I've always thought of like a hypergraph without edges or just unary edges, right? That's to put it in a very hypergraph native language. A hypergraph that is just let's call it a one hypergraph, just unary edges. It's the same as a multiset, basically. It's the same as a set in a way, right? Actually, it's the same as a set. And if you allow for multi-hypergraph, a multi-one hypergraph is a multiset. Hypergraph, a one hypergraph, simple one hypergraph is the same as a set mathematically, right? So the way so in a sense, you're automatically, in the realm of set theory, if you just consider that as your data structure. But to me, hypergraphs would allow you to do is they allow for your base informational structures to be richer and to carry some sort of to be vertebrated somehow. It's like to carry some spine inside. That is not just like blobs of things grouped together, but they are blobs of things grouped together and with some informational structure and some kind of combinatorial structure. So that's how I've been thinking about hypergraphs. Actually, after yesterday's live stream with Nick, I am going to rewire my thinking a little bit because we need to think really hard about what it means exactly to rewrite hypergraphs in our setting. And actually, the conversation with Nicholas next week in the workshop is going to be super useful. So I'm actually meeting Steven next week early and then having that meeting. So I'm going to work quite intensely on just what it means to rewrite. I think we are at a point where I said in yesterday's live stream that we should probably rethink carefully what we mean by rethink. I don't mean change dramatically anything necessarily, but we really need to understand quite deeply because we can't go out in the world and just people say, but how does this rewrite this rewrite framework fit in this existing mathematical expressions? And I've always said we just don't care, it just works or it does the thing that we want for us and things like that. And I think we need to mature a little bit from that. But so anyway, my point is hypergraphs seem to have a native language that is a bit alien, and we want to understand.
I agree with that. So I think what resonates with me there is the fact, or what you were saying in terms of very simple versions of hypermatrices and hypergraph rewriting can give you numbers and sort of simple algebra, but the hypermatrix rewriting gives you so much more, just very basically in terms of higher arity. So this could open up, if this is a decent substrate with which to do existing mathematics, can you imagine how much new mathematics we could do just based on how easy it is to increase the arity and that sort of thing.
That's the promise. I would say that's a very good summary of the promise of hypergraph land, where if you are able to design an architecture that will recover conventional mathematics, then you're safe to just go with not recovering conventional mathematics, but nonetheless doing good work in a sense. That's a good way to put it.
Yeah, and the connections to biology there were interesting as well, because that seems to be a very difficult thing to do in conventional computation. So if there's a way we could optimize the computation here, which is natural for these statistical biological processes, maybe even quantum mechanics, I don't know, Nick, what do you think? Like, do you think that hypergraph computing might be a better substrate to compute statistical versions of quantum mechanics?
Well, Nick, wouldn't you agree that that's part of the point of the physics project?
Well, it's not going to help you to... I doubt there's like an actual physical manifestation of hypergraph computing that can compute the quantum one built on actual physics. But basically, I don't think there's going to be like this classical simulation that's going to just replace or be better, unless there is actually some fundamental thing that allows us to not use quantum computers, but just use classical ones. We just don't know it yet. So there's some quantum-inspired algorithms that we can perform classically, just basically as good as doing quantum directly. And maybe hypergraph can help us.
My point was more Nick, that wouldn't you say that one of the main goals of the physics project, or at least that part of what now is the physics project, is trying to think about hypergraph rewriting rules in this disembodied sense, which I wouldn't even call classical, because in a sense it's informational. It lives in some abstract sort of computational space. It's in the point to recover quantum effects simply in that setting where you have like definite informational structures, and you can instantiate observers, and you can get something like quantum uncertainty or quantum evolution and things like that.
Sure. Yeah, just to develop fundamentals, or all the foundation of the quantum physics, general relativity physics, just all the physics based on just this simple principle. What if under all of it is just kind of computation, and just hypergraph rewriting is the computation of this very general form that is very useful.
Yeah.
Just to interpret all of the.
Yeah, I will. Absolutely. And I would say something even a little bit further. I would say that what the physics project has been attempting to do was to recover very specific kinds of mathematics that are somehow nature inspired, or you could call like almost like reality inspired mathematics, or reality inspired computing, right? Like when you say like biological inspired computing or something. And I would say that you were trying to recover those kinds of mathematics because really you were matching your hypergraph rewrite systems with the mathematics of physics. You were not directly extracting experimental predictions out of the rewrite systems and then going out to an experiment and checking, right? So you were really saying, I have developed this infra-mathematical framework that allows me to recover a formalism, and then that formalism we know that accounts for reality in a very efficient way, right? Of course, the physics project has made other claims, like has made claims of the form, this is more kind of a model of reality that we're proposing. But a lot of the efforts, the actual efforts in the project have been to recover things like manifolds, or recover things like an observer space, or something like a causal structure in space-time, and so on, right?
Yeah, and quantum phase. Yeah.
and yes, and quantum phase and all those things. Yes, exactly. So those are mathematics, right? Those are made of mathematics. Like the way you understand, quantum phase is not a chunk of reality, right? It's not a blip in a detector. It's not an uncertainty of measurement. It's just a mathematical construction that we know very effectively captures those quantum effects. So my point is that I think our mission at the Institute right now is shaping increasingly more clearly to me, and after conversations with Stephen as well, is increasingly shaping up to be this I think very natural position to be, which is that we have a proposal of a way to provide a foundation for computation that is, as you said, this hypergraph rewriting, which is extremely flexible and general. And as long as we can fish out of this huge ocean of possible computational processes that are in many cases unintelligible for anything practical or anything understandable for a human, if we fish out the effective mathematical engines, so to speak, or the mathematical beings that we are used to, then we will be sort of vindicated that, okay, we can now use this in a more native way, or just like go and operate at that level and relax a little bit our mathematical requirements, like which feels more like letting systems evolve, and having generative systems take a little bit more agency in processes, and you as a user are less of a sort of obsessive manager and more like a companion that like you follow along with the system and you see what it does, and then you look at your observations and you see how much they match, and you make anyway. I think that's something that we are naturally following into, and it's an exciting position to be. Obviously, this is I don't want to oversell what I do, because I tend to have perhaps unlike others in the Wolfram sphere, tend to have a pretty understated sort of state of affairs, where I'm always skeptical. Things are not going to work, things are going to fail. But I think this is a very exciting position to be in, right? Like the possibility of rediscovering what we mean by doing mathematics in a way, right? And I don't think it's an overstatement to say that we are essentially providing different ways of doing mathematics. If so far you did matrix multiplication with these kinds of definitions, and what I'm giving you is an entirely different framework where your process is different, where the machines that run the thing need to simulate different things, or even maybe run on a different architecture altogether, then clearly we are providing something that's different. So we don't have a claim of being succeeded at solving something very difficult or being better at something that from a previous framework, but certainly there's a lot of novelty here, and there's a lot of promise in the flexibility that the system seems to allow. Right? So, so Kalei Fisher is saying an analogy with computing using fluid mechanics. That's kind of the spirit here. Absolutely. I've always been fascinating with using physical systems as computing engines, right? And of course, that's what we do in practice, right? Like an actual digital computer just has the transistor is a physical thing, right? It's not a God-given platonic object that we just put in our chips, right? It's just it's a piece of matter, and as any other piece of matter, if we arrange things carefully, they seem to do computation for us, right? That's what we seem to get, and basically the different ways in which we can process things, and it's just a promise of new possibilities, right? It's exciting, very exciting.
I had a question for Nick. When we're doing the physics project, or if you just think in terms of trying to simulate quantum mechanics, is it enough to just have multi-way systems of rewriting rules, or is there something specific in terms of hypergraphs with these hyper edges that allow us to create some of these quantum effects? Like, in other words, could we simulate this stuff with multi-way systems if it was just a normal graph?
Well, originally, it seemed like this is enough. It's like you can at least but on a very high level. It's like you can take the multi-way system, and branch of graphs can, in a way, make some kind of geometrical space that reminds you of the same Hilbert space, the limit. So you can take this kind of argument, but it's not very satisfactory, right? So you actually want to recover the probabilities and phase from the structure, and at least the path counting of the multi-way system can recover probabilities pretty easily. The only problem I see that's you can't recover the phase, and the only element of the phase is just the negative sign. It's like minimal element that's required to be extracted, and I don't know how to make it in the most simple way, to derive the sign that will allow for this destructive interference that you see of probabilities, right? There's like a different approach in how you can recover the probabilities from rewriting systems. Instead of path counting, you can actually impose the statistics by the actual ensemble of your hyperedges. So your system contains all the statistics. It's like, so it's an actual ensemble and a bunch of hyperedges. Just by counting them, you can encode any kind of distribution, right? I don't like this approach, but I think at least this can be, in principle, also recover the quantum effects in the limit when the distribution is actually encoded by many species of hyperedges. So
is that related to increased probability because there's increased degrees of freedom from going between steps? Was that the idea with the path counting? So if there's more ways to get from a certain step to another step, that increases the probability that it will happen? Or what was the idea with the path counting that represented probabilities? So
I understood the question.
Exactly. There was some thing I was reading about where if there is more possibilities for something to go a certain way, then you increase the probability that it will go that way. So there's like this connection between degrees of freedom, or like possibilities. Like the more possibilities that exist for a certain path to be followed by a photon, for example, then the more likely So, I mean, just very simply, if there's a double slit experiment and it can go through slit A or slit B, and there's more ways that it can go through slit B, then it's more likely to go through that direction. So I was wondering if that was connected to path counting, because if there's more paths, then there's more possibilities. That's how
it's all connected to that. It's connected to the path integral formulation, right? If you have just the initial state and the final state, how would you compute the probability of that particular final state happening, the amplitude, and subsequently the square root of that and the probability? You just count all the possible paths from your initial state to the final state. They're going to have some associated amplitude to it. Or if you turn anything into probabilities, it's going to be some probability or negative probability with the sign. And then you sum them over. So some of them actually, because they have negative sign, has to destructively interfere with each other. Right? So they actually do behave some kind of this, have this wave behavior.
I see.
Right? But the multi-wave system doesn't give you this effect for free. Right? Unfortunately. It's like there's no natural way of just for this phase to be emergent in any way. You have to like put it somehow by hand, almost like, right? There's no natural way. I don't know of a natural way to do it.
Okay, well, that's something that might be worth exploring. Was that the idea for Friday, or have we got something else lined up for the Friday session?
Kind of, yeah. We will be exploring this particular issue exactly, just on the example that mostly haunts my mind recently, because this kind of problems only can be explained in some particular example when you deal with locality and realism, and you want to actually a complete example when all of this works together, not just explaining double slit experiment. It's not going to be enough. You have to like resolve the CHSH experiment with this kind of formalism, when two local systems interact and how the destructive interference happens between them, right? And that's the problem. I don't know how to do it, but I at least can explain the problem.
That's a start. In posing the right question is always the right place to start. If you can get to a formalized question, you can actually make progress. Without understanding the problem, yeah, you're gonna be stuck in the wilderness for a long time. It's very true. There's some comments here. Kelly was saying, let me say that always growing from a single point is a very strict box target, then from a random distribution and the graph linking itself together. Gravity is things falling together. Very large physics model. Gravity is things falling together. I guess falling would imply that you have like a space with which you can define what's falling and what's rising. Yeah, gravity is a whole nother thing. That's an interesting concept. And was there any progress in terms of understanding gravity in hypergraph rewriting? Was there a natural way to bring that into place, or not really? We just look at the physics of general relativity.
Yeah, just look at the produced causal graph, and then you say, okay, that's just. Then we borrow all the results from causal set theory. That can derive the Einstein-Hilbert action and actually encode all of the general relativity into it. Interesting.
Yeah. No, that's very interesting, and I like to phrase it that way because that clarifies it even to me, that I haven't had it so clear in my head that the hypergraph rewriting is simply a way to provide the causal sets to begin with, right? And there's already this program where causal sets were considered as a starting point, and then they developed and did a lot of the heavy lifting necessary. This goes in proper Wolfram Institute fashion, sort of infra to that, and we provide a framework to generate those causal sets. Is that picture in your head, Nick? Is that how you see it?
Yeah, that's just called algorithmic causal sets. It also was the idea long before the Wolfram Physics project. Just actually have a way to generate those, because causal sets originally were just, okay, we have a causal structure laid out somehow, and then we just explain what kind of geometry it has by just causal linking, by just the actual connections, nothing else, and some volume element. You can deduce all the Einstein equations and all that from the simple combinatorial structure of the causal graph.
Okay, that makes more sense. Very cool. All right, so that's basically the what's up at the institute, where we've been going basically from the beginning of this year to what's happening next week. So as we mentioned, we got this quantum work happening on Friday, where we're going to specifically take this example of the CHSH game, which is basically a way to think about Bell's inequality. And then next week, Monday, Tuesday, Wednesday, is Hypermatrix workshop. So that's going to be our main focus. Are we planning on doing any live streams next week as well, or we're going to be live streamed out with all the Hypermatrix workshopping?
We're going to have a lot of airtime, because obviously we're going to be live with this, and I'm going to be there. I'm going to be hosting myself most of the live streams. So I personally don't think we'll have the time, because I will be either running those or traveling. But do expect, if you guys want to meet to talk about quantum stuff, there's that coming. And we should also mention that the Wolfram Summer School is still, I think registration is still open. I will give you some introductory materials there if you do participate. Yeah, it's very exciting times.
Yeah, so Wolfram Summer School starts on, there's 2 streams this year, but we'll pop the link in here, but we're looking at June 23rd is the first stream starting. So yeah, definitely jump in there, and it's definitely a once in a lifetime opportunity to do something like that, although you can attend multiple times if you try hard enough. So yeah, that's great. Okay, cool. So that's an hour of just chatting and updating. Is there anything else that's on the agenda that you wanted to chat about for now, or should we?
No, I'm quite satisfied here. I wonder if anyone in the chat has any comments or questions. Oh, there's one thing I wanted to mention. Yes, before we go, I want to highlight and give a shout out to Sam Rotke, one of our community members. This guy really is going, above and beyond what a community member is expected to do. But I really want to bring it up here on the live stream so people can see. Let me maybe share it in the Discord briefly. So Sam has been very interested. I don't think he participated in any of the live streams yet, in the sense that he was not in the chat. But he was very early on curious about, and I just want to just document what happened, because in a sense it's a testament to what we want to achieve with our community, and the fact that it already happened in this sort of organic way is really encouraging, and it really warms my heart in a sense. So I think you scroll up. This is, by the way, this is the infrageometry channel. So I was just making some notes from our live streams. This is when we were so confused about what functions were and things like that. Which, by the way, we have just moved the worry to some of the place. We haven't really resolved these issues fully, but it feels like progress now. At least it feels like we are. I understand some things better today than I did 2 weeks ago. So it's a good thing. And then Sam essentially just said, "Oh, very interesting. I have, forgive my words to say." It was very, very, very polite and very interesting in our project. And so he started making this graphics and explaining how you could interpret different rewrite rules. And at this point, it were just graphics that were being drawn, in some sense, hand drawn, right? And then we discussed about unary edges, and I was saying these loops can just be encoded by some kind of unary edge information, and then he was himself just giving these essays, which is we really appreciate this level of details. They were very well written. You can read through them and you can really understand what he was thinking. He posted the analogy with flow network models, which is something that we mentioned a few live streams ago. Then he goes on and actually simulates the process. So this is a GIF. You can see there's an animation where there's a concentration of something like this, right? You have a concentration of unary or self loops here, and then as you apply this rewrite rule where you move when there are two self loops, you move to one to the other, which is more or less the same as applying this rule that we had up here. You just move a unary edge along a binary edge, and it's really cool. I mean, he created the simulation, so you can see the actual stochastic application of rewrite rules. And then, of course, he got some nice ideas about attractors in rewrite systems. And then eventually, he actually started to use our packlet and started dipping his toes in our packlet. So there's some analogy with the heat equation and the diffusion of these rewrite rules. And so these are his own attempts at running our hypergraph packlet. So I guess this is the first person that actually is trying to make use of our packlet, which is great to see. And there's also a lot of things being asked here in support and help, where he's been running some things and Nick detected some issues and we updated. So anyway, I just want to give a massive thanks to Sam Rocky for this level of engagement, not only because it's a good example for others to follow, and that's how we want to encourage people to interact with us at the Institute, but because the input itself is very good, and we've spotted some issues, and it is properly contributing to what we do. It's not just sort of fun and entertainment. It's really quite valuable. So we're very happy about this, and I just wanted to make sure that we shout out to this guy, because it's been great. So this is very much what we are here for. If you want to get excited and take on some aspect of the projects, that's why we do open science. I mean, I'll just take the opportunity to say that's exactly the purpose of open science, right? That you don't need to be an expert, you don't need to be affiliated with an academic institution. Everything we do is publicly available. We will publish our results, intermediate results, we will publish our notebooks, and all of our infrastructure is out there for you to use. And in that sense, we are perhaps following in the footsteps of the Wolfram tradition in this sense, in terms of tooling and providing resources. But this is now science. This is now pure research, and everyone is welcome to join the conversation.
Yeah. Okay, great. Sounds good. I think it would be nice to have some more of these community subforums. There's some interesting developments that can maybe talk about in terms of maybe latest discoveries or publications that will be worth discussing. Just two that comes to mind, which we can maybe earmark for next time. The one is on some additional evidence that leads credence to Stuart Hameroff, I believe, and Roger Penrose's idea about proto-consciousness that was extracted from samples on the asteroid Bennu, which is returned to Earth. So that's like very interesting, and that like their whole angle is that it wasn't life that led to consciousness, but it's the other way around, and it's like a fundamental property of the universe. So that's like a very cool profundity type direction. And then the other thing which was quite interesting I was reading yesterday was this paper published on thinking about observers and having a model for an internal observer and an external observer, and why there's an importance to having these two different types of observations, almost like who's the observer inside of a photon and then who's the observer outside of the photon, and how there's these interesting dynamics. So I'm going to read that paper in a bit more detail, and maybe after that we can have some discussions on that. So there's a lot of interesting ideas and angles that, apart from what we're specifically researching, just applying our minds to some broader topics might be informative as well. So yeah. And if anyone else finds interesting things that they would like, to have us ponder, please share it on the Discord, and we can bring it up on a future community forum. Cool.
Yeah, I will just bring up once more, as I always do, how to get into the Discord in case we have some viewers that just joined for the first time. You just follow to our website. Let me get the link. I can't get the link at all. I don't seem to be able to get the link. Interesting. So we'll just get the link very quickly.
And then also, while we're thinking about future streams, continuing the explore and learn, there's still obviously a lot to explore and learn, but I think the last place we left off was next to discuss rewriting. So we spoke about the fundamentals of hypergraphs a bit, and then what is it actually fundamental about rewriting itself. So that's also on the agenda for a future explore and learn session. So
yes,
yeah, I'm quite keen on that.
Exactly, and next week you will get the technical side of things. But next week we're gonna be talking a lot about hypergraphs, rewriting, algebras, hypermatrices, all these technical, the mathematical technical side of what we do at the Institute. But rest assured that in following weeks we will do explore and learn. We will do in the Wolfram Summer School, I will be presenting an introduction to hypergraphs with the hypergraph Padlet, and generally we're going to be engaging with our community to as Sam Rutke did and just highlighted, to keep improving the tool and to keep progressing all together. So this is a good objective to keep in mind.
Great, sounds good. Okay, any parting thoughts, Nick, from your side?
No, I'm good.
I like putting Nick on the spot. Okay, great. Thanks, Carlos and Nick, for joining us. And yeah, next session will be on Friday. We're going to do some more quantum stuff. Chat to you then.
Thank you, everyone.
Okay, bye for now.